Okay, let us take up successive differentiation. I hope you have already done successive in your 12th, so I will be starting with Leibniz theorem. It states that if u and v are any two functions of x, which can be obviously which are differentiable up to nth order, then we can find their nth derivative uvn. This is the nth derivative of their product. It is nc0 unv nc1 un minus 1 v1 nc2 un minus 2 v2 plus so on ncn uvn. See, if you have, we prove this theorem with the help of mathematical induction. If you have uv, two functions which are functions of x, y is function of x, but this is the product. So if I will find y1 derivative with respect to x, means I have to differentiate this with respect to x. What I will get? u1v uv1. Derivative of u is u1, v as it is, then u as it is, derivative of v is v1. This can be written as 1c0 u1v 1c2 1c1 sorry uv1, because 1c0 is 1, 1c1 is NCR. NCR is factorial n factorial r factorial n minus r. You can use it. So 1c0 is 1, 1c1 is 1. Let me differentiate it again with respect to x. What is y2? These are two functions. Let me differentiate first these two functions. U means u1 means u2, v as it is. u1 as it is, derivative of v is v1. Then we have now these two functions. U means u1, v1 as it is. Then u as it is, derivative of v1 is v2. Or this is u2v twice u1 v1 plus uv2. Or this can be written as 2c0 u2v 2c1 u1 v1 2c2 uv2. 2c0 is 1, 2c2 is 1, 2c1 is 2. So this shows the result is true for n equal to 1. This shows that the result is true for n equal to 2. You can have 2c0, 2c1 and so on. Now let me assume that the result is true for n equal to m. Means uvm mth derivative is equal to mc0 umv. Instead of n we have m. mc1 um minus 1 v1 mc2 um minus 2 v2 mcm uvm. Since I have already told you that we will be proving this with the help of mathematical notation, I have shown that result is true for n equal to 1, n equal to 2, and I have assumed that result is true for n equal to m. So I have to prove that result is true for n equal to m plus 1 also. So for that, let me differentiate this with respect to x again. These are all functions of x, but in terms of product. So derivative of uv, this is the mth derivative. Its first one more derivative is um plus 1. This is mc0. This is umv1. We have to differentiate it once. So this is um plus 1. V as it is. Derivative of v is v1. Then you have mc1 v1. Derivative of minus 1 is v1 as it is. Then minus 1 as it is. Derivative of v1 is v2. Then mc2. Derivative of minus 1, it is minus 2, it is minus 1 v2 as it is, um minus 2 as it is, derivative of v2 is v3, plus so on, mcm, u as it is, derivative of v, or u is v1 vm, then you have u as it is, derivative of vm is vm plus 1, vm plus 1. This is it. Now let me combine them. This is mc0 um plus 1 v1 v, then mc0 plus mc1 um v1. This is um v1, this is um v1. So this is mc0, this is mc1. Fine. Then you have m minus 1 v2, m minus 1 v2 here. So mc1 plus mc2 um minus 1 v2, plus so on, mcm uvm plus 1. Fine. This is m plus 1 c0 um plus 1 v. Because mc0 is 1, m plus 1 c0 is 1. So I can replace mc0 by m plus 1 c0. Now you have one more thing. Let me write it over here. mcr plus mcr minus 1. It is m plus 1 cr. You can check it. So let me write down. This is mc1. mcr means mc0 plus mc1 is m plus 1 c1 um v1. mc1 plus mc2 is m plus 1 c2 um plus 1 v2, plus so on. cm is 1, so m plus 1 cm plus 1 is also 1, so I will replace mcm by m plus 1 cm plus 1 uvm plus 1. I hope you understood that mc0 plus mc1 is m plus 1 c1. If you don't, let me show it here. nc0 nc1, it is factorial 0 factorial 1 factorial n factorial 1 factorial n minus 0 factorial nc0 factorial 0 factorial n factorial 0 factorial n minus 0. So this is it. Then factorial n factorial 1 factorial n minus 1. So this is nothing but 1. This is factorial up to n 1 2 3 up to n, means 1 2 3 n minus 1 n, means factorial n minus 1 into n. So it is n only, because factorial n minus 1 will cancel out. Now what about m plus 1 n plus 1 c1? It is factorial n plus 1 factorial 1 factorial n. So this is again n plus 1. So both are equal. That is why I have replaced mc0 plus mc1 by m plus 1 c1, mc1 plus mc2 by m plus 1 c2. So this shows that result is true for n plus 1 also. This shows that result is true for n equal to m plus 1 also. Since we have already verified results for n equal 1 2 3 1 2 so on, we conclude that result is true for or n greater than 1. Okay, in fact greater or equal to 1, because we are finding y1 also. So this shows result is true. For example, question, this is page number 39. Page 39. Page 40. Page 40. Now, let me take a question. Say, simple question. Y equaled x raised power 3 and e raised power ax. You know what is the derivative of e raised power ax? Another derivative. It is a raised power n e raised power ax. Fine. And derivative of x cube, if we can differentiate it up to third derivative only, fourth derivative will be 0, because another derivative of x raised power n is factorial n. So n plus 1 will be 0. So I will keep this as u, this as v. V is kept, that function is taken as v, which differentiates, which terminates after some time. Okay. Now, this is u, this is v. I know by Leibniz theorem, nth derivative of the product is nc0 unv nc1 un minus 1v1 nc2 un minus 2v2 plus so on ncn un minus un uvn. Now nc0 is 1, un and the derivative of this u, it is a raised power n e to the power ax. And v as it is, what is v? V is x cube. Fine. Then nc1, what is that? N. nc1 is n, factorial n, factorial 1, factorial n minus 1. N minus 1, the derivative of this function is a raised power n minus 1. You have to replace n by n plus 1, n minus 1 only. E raised power ax, and first derivative is 3x square. Then nc2, n into n minus 1 by factorial 2. You know it. A raised power n minus 2, second derivative is 6x. Then n into n minus 1, n minus 2, factorial 3, a raised power n minus 3, e raised power ax, e raised power ax into 6, and then this will be 0. So you will conclude up to this only. So the solution is e to the power ax, rest you can take it as it is, a raised power n x cube and a raised power n minus 1, in fact 3x square, n into n, what is n? N is 3. Oh, your n is 3 na? And then you have to take n the derivative, n into n minus 1 factorial 2, a raised power n minus 2, 6x, and n minus 1, n minus 2 factorial 3, a raised power n minus 3 into 6. You can simplify it further. So this is it. Fine. Another question. Let me take y equal to x square log x. Say this is u and this is v. What is n the derivative? This can be written as yn also. Yn. This is nc0 log x and a derivative x square as it is. U and a derivative as it, v as it is. Then nc1 log x n minus 1 a derivative, first derivative. nc2 log x n minus second derivative and second derivative of 2x, which is 2, and we cannot go beyond this. Now you know what is the n derivative of log x? Yes, it is minus 1 raised power n minus 1 factorial n minus 1 divided by x raised power n. This you already know. So what will be n minus 1th? It will be minus 1 raised power n minus 2 factorial n minus 2 x raised power n minus 1. What will be n minus second? Minus 1 raised power n minus 3 factorial n minus 3 x raised power n minus 3. So on. So let me write it. This is nc0 minus 1 raised power n minus 1 factorial n minus 1 x raised power n and x square plus nc1, it is n minus 1 raised power n minus 2 factorial n minus 2 x raised power n minus 1 2x. Then n minus 1 by factorial 2 minus 1 raised power n minus 3 factorial n minus 3 x raised power n minus 2 and 2. This is it. Fine. Let me take one more question. Y equal to x cos of x. You know cos derivative of, so n derivative of cos, you know first derivative of, let me keep it x square. This is u and this is v. So what is the n derivative? nc0, it is 1, n derivative of cos x square. NC1, it is 1 cos x, n minus 1 derivative, first derivative, NC2, n into n minus 1 by factorial 2 cos x, n minus second derivative, n2. Now you can substitute the value of n derivative of cos, which is cos of x plus n pi by 2, then x plus n minus 1 pi by 2, n minus second pi by 2. So write down x square cos of x n pi by 2, then n 2nx, we can write 2x and n cos x plus n minus 1 pi by 2, then 2 and 2 cancels out, n into n minus 1 cos x plus n minus 2 pi by 2. This is it. So this way you can use binomial expansion to find the product of two functions. Now let me take up few more questions. This is page 41. Page 41. Now let me take say y equal to sine inverse x. I have to find y n plus 2. yn plus 2, or a relation in terms of yn plus 2. For yn plus 2, I need to find y2 first. Then if I will differentiate y2 n plus n times, I will get n plus 2. So let me differentiate first with respect to x. Differentiate with respect to x. I will get y1 equal to 1 upon under root of 1 minus x square. Fine. Or let me write it as sine inverse x whole square. So this is twice sine inverse x, 2 sine inverse x, and then derivative of sine inverse x is 1 upon 1 minus under root of x square, or under root of 1 minus x square y1 is 2 sine inverse x. Fine. Or I can square and let me square on both sides. I will write 1 minus x square y1 square equal 4 sine inverse x whole square. Now what is your sine inverse x whole square? It is y. So I have 1 minus x square y1 square equal 4y. Fine. Now I have to find y2 because I have to find yn plus 2. To find yn plus 2, I need to find y2 first. So let me differentiate again with respect to x. 1 minus x square as it is, derivative of y1 square is twice y1, y2. Then y1 square as it is, derivative of 1 minus x square is minus 2x. And this is 4y1. Or you have 2y1 here, 2y1 here, 2y1 here. 1 minus x square y square. Fine. Is it okay? 2y1 y2. This is y2, not y1 square. Derivative of y1 square is twice y1 and derivative of y1 is y2. So this is y2. Now this is 2 cancels out. So this is xy1 equal to y1. Because I have taken 2y1 common on both sides and I have cancelled it. Or you have 1 minus x square y2 minus x minus 2 or plus 2y1 equal to 0. Fine. Let me check it again. This is 1 minus x square. Derivative of y1 square is twice y1 y2. Then y1 square as it is. Derivative of this is minus 2x. 4y1. Now I have taken 2y1 common, so it is only 2. Only 2. Because 2y1 is gone, 2y1 will cancel out on both sides. I will write 1 minus x square y2 minus x y1 minus 2 equal to 0. This is it. Now I have to find yn plus 2 or a relation within 1n plus 2. Let me differentiate this with respect to x n times, or let me use Leibniz theorem. This is the product of functions 1 minus x square and y2. I will keep y2 as u and 1 minus x square as v. Now let me see what will be the differentiation. This will be nc0 y n plus 2 derivative of y2 with respect to n. And the derivative of y2 is yn plus 2, 1 minus x square is as it is. This is u, and the derivative, and v as it is. Then plus nc1 n plus 1 first derivative n into n minus 1, okay, nc2 yn, and one more derivative is 2. Khatam. Now you have minus times x and y1. Now your x is v and y1 is u. So nc0 yn plus 1 x as it is. Then nc1 yn x. You have two functions x and y1. Derivative of y1 is yn plus 1, and its first one more derivative is yn only. Okay. Then x and derivative of x is 1, sorry, and this is 0 equals 0. So it is 1 minus x square yn plus 2 because nc0 is 1, minus 2 n x yn plus 1 because nc1 is n. Then minus 2 n into n minus 1 factorial to yn, minus nc0 is 1, yn plus 1 x plus minus n yn is equal to 0. Fine. Now let me combine them. This is 1 minus x square yn plus 2. Yn plus 1 is over here. Yn plus 1 is over here. Minus. X is common to them. So this is minus times 2n plus 1 yn plus 1. Okay. 2 and 2 cancels out. This is minus n square plus n. Minus n square plus n yn. And this is minus yn. So let me take yn common. Equals 0. I have taken, see, now I will write it like this. I have taken minus common. Minus is over here. Minus is over here. This is n into n minus 1. So this will be n square minus n. And this will be plus n because I have taken minus common. So what remains is finally 1 minus x square yn plus 2 minus 2n plus 1 yn plus 1 minus n square yn equal to 0. This is it. You have a question on your book where you have been asked to prove that for y equals sine inverse x whole square, prove that 1 minus x square yn plus 2 minus 2n plus 1 yn plus 1 minus n square yn is equal to 0. My assignment is, home assignment is that you find yn at 0 and the derivative at 0. Fine. You have to put x equals 0 and you will find a relation. This is for page 41. Let me take up page 42. And let me take up a question from here. Question is, y is equal to sine m sine inverse x m sine inverse x. You have to prove that 1 minus x square y2 minus xy1 minus or plus m square y is equal to 0. And then a relation in yn plus 2. Now let me see how to proceed. You have y equal to sine m sine inverse x. This means sine inverse y is m sine inverse x. Let me differentiate. This is 1 upon under root of 1 minus y square, derivative of y is y1, is m 1 upon under root of 1 minus x square. Let me square and differentiate, I will get, and cross multiply, I will get y1 square, okay, y1 square, let me first square it, 1 minus y square equal m square 1 minus x square, or 1 minus x square y1 square equal m square 1 minus y square. Or now let me differentiate it with respect to x, because I have to find a relation in terms of y2. 1 minus x square as it is, derivative of y1 square is twice y1 y2, minus y1 square as it is, derivative of 1 minus 2x is minus 2x, so it is 2x, minus I have already taken. This is m square minus 2y y1. Now again 2y1 is over here, 2y1 is over here, 2y1 is over here. So what remains is 1 minus x square y2 minus xy1 see this is y1 square, okay, plus 2m square y equals 0. 2m y1 cancels out, 2y1 cancels out, it is xy1 over here, and this is minus 2 minus m square y, 2 cancels out, so minus plus m square y. This is it. This I have shown, this I was supposed to show. I have to see a relation in terms of yn plus 2. For that I will use Leibniz theorem. Apply Leibniz theorem. See, this is u, this is v. So this is yn plus 2, 1 minus x square as it is, then n, yn plus 1 minus 2x, then n into n minus 1 factorial 2 yn. This is first one. Second one is x yn plus 1, then n yn, derivative of x is 1, plus m square yn equal to 0. Or 1 minus x square yn plus 2 minus 2 and x yn plus 1, derivative is 2, I have not written it. See, this is x yn plus 1 minus 2x, then nc1, n into n minus nc2, n into n minus 1 factorial 2, yn plus 1 means yn, derivative of minus 2x is 2. 2 and 2 cancels out, so it is n into n minus 1 yn minus x yn plus 1 minus n yn plus m square yn is equal to 0. Now let me add up the things. 1 minus x square yn plus 2, yn plus 1 over here, yn plus over here, same as was in the previous question, 2n plus 1 x yn plus 1. Then you have n square minus n yn. This is minus yn. Is it okay here? Oh, derivative is, see, derivative, first derivative is 1 minus x square is okay, then derivative is minus 2x, then another derivative is minus 2, so minus will be over here, so it is minus n square plus n minus n yn. Let me write it as y square and yn minus n square yn plus m square yn is equal to 0. This is n square minus plus n and minus n. So this goes. What remains is 1 minus x square yn plus 2, 2n plus 1 x yn plus 1, then m square minus n square yn is equal to 0. This is it. This was, you were asked to find this. I will show one more not I will not show it fully, but I will just help you. This is 1 raised power 1 by m plus y raised power minus 1 by m equal to x. You have to find a relation in terms of yn plus 2. Let me suppose that y 1 by m is z. Let me put y 1 by m equals z. Then what I will get, z plus z raised power minus 1 equal to x.